Okay, this lesson is for Mrs. Cucci's College Now Pre-Calculus class. We are on lesson 6.1b, so we're going to pick up where we left off. So what we were talking about is we were talking about simplifying trigonometric identities or expressions. So we're going to continue on with that. We left off on example 3, and we're going to pick up on example 4. So make sure you have your notebooks out as you are taking your own notes today. Okay. So example 4 says to add and simplify. Okay, we're going to add and simplify cosine x over 1 plus sine x plus tangent x. Alright, so what I want to do is I want to try and adjust this so that I can get to as much of a reduced form as I possibly can. Okay, so the first thing that's really jumping out at me is tangent, because I know I can probably adjust that. Also, this 1 plus sine x looks somewhat familiar, and I'm thinking maybe I can adjust that as well. Okay, so what I'm going to do is I'm going to start by adjusting that tangent. And we know tangent is sine over cosine. Okay. And since I'm adding fractions, I probably am going to want a common denominator. So my common denominator, again, would have to be the product of my current denominators. So cosine x over 1 plus sine x. And I would have to multiply that by cosine x. Plus sine x over cosine x. And I would have to multiply that by 1 plus sine x. Okay, we want to get common denominators. Alright, so now I'm going to have to go through and multiply this out. So, in the numerator, we're going to wind up with cosine squared x. And in the denominator, I do have to distribute. So that's going to give me, well, actually, let's leave it in undistributed form because we've got going to have the same thing on the other fraction as well. Plus, we do need to distribute here, sine x plus sine squared x over, and I'm going to leave it undistributed here as well. Okay, so the next thing I'm going to do is I'm going to combine this so that I have it as a single fraction. Cosine squared x, and I'm going to change the order here, and that's okay since addition is commutative. Sine squared x plus sine x, and that's over cosine x times 1 plus sine x. Okay, so something should be jumping out at you here. Hopefully you saw this and thought, that's Pythagorean identity, I know what that is. Cosine squared x plus sine squared x is equal to 1. So I can adjust that to 1 plus sine x. Okay. Now something very nice happens here. 1 plus sine x and 1 plus sine x are going to simplify to be 1. And I'm going to have 1 over cosine x after that simplifies. And we know that 1 over cosine x is equal to secant x. Okay? Alright, so we were able to add and simplify. Alright, so let's look at another example. This is going to be example 5. An example says multiply and simplify. And we're going to multiply and simplify square root of sine cubed x cosine x times the square root of cosine x. Now, when radicals occur, we're going to use the use of the absolute value sometimes is necessary. It can be tough to figure out when to use it. So we're going to assume that all the radicals are non-negative. This means that the identities are going to apply to certain quadrants. Okay, so we're going to assume that they're non-negative. So we've got two radicals. We know how to multiply radicals. When we're multiplying radicals, we simply multiply the radicands. So when we multiply this together, we wind up with sine cubed x cosine squared x. Okay. And what I'd like to do next is kind of break this up. I know that cosine squared x is a perfect square. Sine cubed is not, but we can break it down so that its factors, one of them is. Okay? So I can say that this is sine squared x times sine x, because we know that's sine cubed. And then I still have my cosine squared x, and I know I lost my line here. So I know the square root of sine squared x is sine x, and the square root of cosine squared x is cosine x. And then all I'm left with underneath the radical is sine x. Now, there doesn't seem to be anything else that we can do here, so that's about as simplest as it's going to be. So that's the answer for this one. All right, so let's look at example 6. And this is going to be rationalizing the denominator. Okay. And it's going to be radical 2 over tangent x. All right, so when we're rationalizing the denominator, we know that we need to multiply the denominator of the fraction by something that turns it into a perfect square. Okay? So, what we're going to do, in order to turn tangent x into a perfect square, why do I keep losing my n here? Oops. Is we're going to multiply it by tangent x. Okay? And remember, it's a fraction, so what we do to the denominator, we must do to the numerator. Okay, so this leaves me with 2 tangent x over tangent squared x. And again, we're rationalizing the denominator, so the goal is to get rid of the square root in the denominator. I know that this is the same as this. Okay. And the square root of tangent squared x is tangent x. And that's rationalized. Okay, so a lot of times in calculus, a substitution is often helpful for us to manipulate an expression. So that's actually what we're going to wind up doing in this next example. Okay, so this is example 7. In example 7, we want to express the square root of 9 plus x squared as a trig function of theta without using radicals. We're going to do so by letting x equal 3 tangent theta. we're also going to assume that theta is between 0 and pi over 2, not included. And then we're going to find cosine theta and sine theta. Okay. All right, so we have to do our substitution. So we're going to start by doing that. So again, we're substituting 3 tangent theta in for x. Okay, we still do need to square it. So when we go and we square this, we wind up with 9 plus 9 tangent squared theta. And then basically what I'm doing is I'm looking at this and thinking about what can I do algebraically to make it look different. And the only thing that I'm coming up with by looking at this is noticing that I have a 9 in both parts of my radicand. So what I'm going to do is I'm going to pull that 9 out as a GCF. By doing that, what I've done is I've uncovered one of our identities. Okay, 1 plus tangent squared theta, we know otherwise as secant squared theta. Okay. And also what I now have underneath this radical are 2 perfect squares. Square root of 9 is 3, and square root of secant squared theta is secant. Now again, we're using the absolute value because we are assuming that it's positive. Okay, so this equals 3 secant theta. Okay, so we can express 9 plus x squared as 3 secant theta. We can also express secant, if we want to get secant alone and say what secant equals, is to divide over that 3. 9 plus x squared divided by 3. Okay, so that's what secant equals. And the reason we did that is in the initial problem, we wanted to find what cosine and sine equaled when we were done. Okay? What I have now is I have secant. Since I have secant, what I can do in order to find cosine is pretty simple. I know that cosine is the reciprocal of secant. So all I have to do is simply flip or take the reciprocal of what secant is equal to. Okay. Another way to think about this, because I do also need to find sine, is to think about this as a right triangle. Pick an angle and call it theta. Secant we know to be hypotenuse over adjacent. So if I want to find sine, what I'm going to have to do is I'm going to have to find my opposite side in order to get me there, because it's going to be our opposite over hypotenuse, right? So I know my hypotenuse, but I need to find my opposite. And of course we can do that by using Pythagorean theorem. Okay. So we get 9 plus b squared equals, when I square a radical, the radical disappears. 9 on each side is going to cancel. B squared equals x squared. Square root. B equals x. So this is going to be x. So now we have sine and cosine. Okay, so the next group of identities that we're going to move on to is the sum and difference identities. I think that I will start sum of difference identities as a new video. So we're going to end here. Make sure that you get the notes done and written down. And I shall see you all tomorrow. Thanks, guys.